Hi and welcome to today's video. Now before we go into the mathematical theory a little deeper, I'd like to at least give you a little motivation for why we are dealing with things like bases of vector spaces. This is an economic application, more of a hint of an economic application to be honest, because it will leave some questions open that will hopefully be answered during this or maybe the next semester in some way or the other. So let's sketch an application where bases of vector spaces play an important role. Let's say you're working for a company in the marketing department, and that department is testing a new advertising platform. What they do is they spend different amounts of money on placing ads on a platform, and then they record the result in terms of increased sales. And the question is, of course, what is the effect of the money spent on additional sales? Can this be quantified in some way? So, the company is testing a new advertising platform. And let's say we're doing this for 6 days. So for 6 days, the company tracks spending for ads on a platform and also the increased sales of a certain product. Now here's the results that they get, and the numbers are more or less arbitrary. But let's say we have spending and we have extra sales. So what we get here is, let's say we spend 1.91, whatever currency that is, and we get extra sales of 3.77, maybe that's thousands of products or hundreds of thousands of products. Whatever you want to imagine here is good. I'll just enter the other data points for you, and then we have a look at what that actually means. 0.46, 1.12, 1.02, 1.94. Then here we spend 2.7 and 1.3. And we obtained 6.15 extra sales and 2.10. Then what we can do is, of course, we can interpret each of these as a point in two-dimensional space in R2. So basically, here's a point in R2, here's a point in R2, and so on. And that means we can reformulate these data in the forms of vectors. We can interpret all these data pairs as points in R2. So what we get is 1.91, 3.77. That's a vector. 1.95, 3.4. That's a vector. 0.46, 1.02, 1.12, 1.94, 2.7, 6.15, sorry, and 1.3, 2.1. But now we have 6 vectors. Well, we didn't win a lot yet. Now, of course, the company would like to know what the effect of the extra advertising on sales is. So what is the effect of advertising on sales? In linear algebra terms, the idea is we can try to find a basis that is more suitable for this. So the current basis that's underlying the system is the standard basis. Currently, the vectors are with respect to the standard basis. Now the standard basis is just 1, 0, 0, 1, the unit vectors. The question is there a basis that kind of isolates this effect better? So the idea behind this is each of those vectors represents a certain deterministic effect that really captures the effect of additional spending, plus a random part that captures random daily fluctuations. So the idea is data points are the result of we'll just call this deterministic part, it captures the real effect, plus a random daily fluctuation. And of course, we'd like to isolate this deterministic part here. And to do this, what we do is we'll express the vectors in terms of a different basis. Now this basis, I'm just going to give you that right away. The basis that we're going to use is B1 is 1, 2, and B2 is 2 minus 1. It's absolutely not clear how to get that basis, and it's also not clear yet what special properties this basis has. We'll get to that point later on in the lecture. For now, let's just take this basis and see what effects we can see using this basis. What happens if we express the vectors in terms of this basis? Meaning, we express each vector as a linear combination of B1 and B2. And what we get here is our first vector, 1.91, 3.77. That is 1.89 B1 plus 0.01 B2. What you can see is this factor here. This is very large compared to this second factor. What that means is this B1 here, that part, is able to explain most of that data, right? It's almost a vector B1 or a multiple of B1. So the correlation expressed in B1 seems to explain most of that vector, with just a little bit of B2 necessary to correct for these random daily fluctuations. And you'll see the same for the other vectors as well. I'll write down the results for you. This is 1.95, B.4, that was the second vector. That is 1.75 B1 plus 0.1 B2. The next one, 0.46 and 1.02. That can be written as 0.5 B1 minus 0.02 B2. Then we have 1.12, 1.94. That can be written as B1 plus 0.06 B2. We have 2.7, 6.15. That is 3 times B1 minus 0.15 B2. And finally, 1.3 and 2.1. That is 1.1 B1 plus 0.1 B2. What you can really see here is this B1 part, this part here. That really is the dominating factor. So the idea is B1 explains most of the data, so to say. It represents the underlying principle, the correlation between those two components of the vector. So this represents the underlying correlation of the data. Okay, that's kind of the long-term effects here. And B2, on the other hand, reflects random daily fluctuations. And as I said already, of course, the hard part here is to actually find a basis that has this property, that one of the factors is large and the other is small, or in higher dimensional spaces, a few of those factors will be large and many, many other factors will be small and represent these errors, these random fluctuations. So the question of how to find such a basis is not at all a trivial one. This kind of decomposition is one, not hard as well. It can be done with the means of linear algebra, and we learn all the means necessary for that. But we're not at that point now. Yeah. So the idea of that application was to give you an idea of where this can all lead and why bases may be important for analysis of data. And that's one of the uses of a suitably chosen basis. And as I said, we learn more about how to choose such a basis and what properties such a basis needs to have later on during this semester and the next one. So I'll see you in one of the upcoming videos then.